Hello. We're going to be looking at section 4.3 here, dealing with basically what we've been doing so far. We're just going to add another stage onto it, another level. So we're looking at the derivative of f and how that relates to the graph. We've basically done that. Now we're going to look at also how the second derivative relates to the graph. So this will be a little bit of new stuff that's going to be very similar to what we were doing before. So to start with, I'm going to make a data table here on the screen that would be a very good one for you to have in your notes, especially for these first three sections. This is basically going to be the main summary of these first three sections all here in one nice spot. So our first thing, when we were looking at this chapter, we started off, we found critical points, those extreme values like maximums and minimums. So just to start off with, how did we find those critical points? What did we do? Yeah. So we took the derivative and we set it equal to 0. That was usually our first step as we were finding these things. And when we solved that, we usually got some values that typically were our maximums or minimums of the graph. And then the next thing we did, we made it like a number line, and we plotted those critical points as well as sometimes any like domain issues. We added those in later, and we looked at the derivative in each of those sections. And based on whether or not the derivative was increasing, so if our derivative is greater than 0, then we have an increasing graph. And if our derivative in that section is decreasing, we have a negative below 0, then we are decreasing in that section. So that was what we've done so far. What we're going to add on here after critical points, another thing we can look at is an inflection point. And I'll tell you what that actually means at some point here in just a second, as well as what would be called concave up and concave down, which are a couple new terms, I suspect. You might have, if you took like physics or in science classes back in the day, you might remember hearing like concave, we're talking about like mirrors or lenses and such. So if I look at a graph, well, let's draw like just a rough graph over here. Let's say my graph looks like, and then it goes like that, and it continues along on both sides somewhere. So when you're talking about concave up and concave down, the way that when you're looking at a graph and you want to visualize it, you can think of your hand being like a cup. And if you have a concave up, then your hand would be facing up. If you're concave down, then that arch is going down. So this is concave down. This is concave up. So if I'm looking on that graph that I drew there, this section here would be where my hand would be a cup that's up. It would be holding water. So that's my concave up part. So I'm going to write that concave up. And then over here, as I get into this part of my hand, I can't really do that. That way I'd have to flip my hand over to have my palm facing down. That's the concave down part. Want to jump to the screen there. Concave down. So basically what's happening is that our slope, as we go from left to right, our slope is increasing. So our slope was very steeply negative, and then it gets less and less negative, it goes to 0. And then it starts increasing, becoming more and more positive. And then at some point right about in here, then my slope now starts to decrease. It starts to get less and less and less closer to 0. So it depends on whether the slope is increasing or decreasing. So that point in between, where basically my fingers would meet up, when I've got the concave up and concave down, that would be my inflection point. That's what we're talking about there. And how we find these is very similar to what we did with our critical points that are increasing and decreasing. It would be the exact same thing, except now with our second derivative. So it would be when my second derivative equals 0. That would give me an idea of where the inflection points should be. Concave up is sort of like increasing. It's going to be when our second derivative is increasing, and concave down would be when our second derivative is decreasing. So you're going to use this general idea here, and you're going to look in your assignment, just a short assignment, 2 questions. The first question, I believe, is showing you the graph. And you're looking at the graph, and you're going to identify where is like that first derivative equal to 0, meaning maximum and minimum. When is it increasing or decreasing? Positive, negative. When is the second derivative? When would that be 0? Where would an inflection point be? Just sort of visualizing where would those parts meet up when you're going concave up and concave down, trying to identify those to get rough estimates. And then the second question, which is actually I think question 4, you're going to be looking at, just to emphasize, a graph of the derivative. So when you're looking at it, you're looking at the first derivative. So just a little hint on that. For the first derivative, if you're looking at when is the first derivative increasing, that's not when the graph is going up. It'll be when the graph is above the x-axis. Anything above the x-axis, doesn't matter if it's going down or up or whatever direction, as long as it's above the x-axis, that first derivative is positive. So it's a little bit weird to think about, getting a little bit more abstract, a little bit more fun, but it's a good questions to look at. So we'll start with just those first two questions, and then we'll come back again and look at a little bit more in-depth example of actually working through and doing this stuff analytically. So good luck with that. Try your best on those ones. Come up with the best you can get on there.